So we'll continue the discussion regarding the 802.11 baseline standards. And we talked last time about different levels to avoid collision. So we talked about the fact that the first thing we do to avoid collision is by performing sensing. So when we sense, we detect whether the medium is idle or not. And then the second level is just to, when we detect that the idle is idle, when the medium is idle, then we have to wait for DIFS to make sure that nobody else is trying to access the medium at the same time. And even then, we cannot eliminate collision. So the third level of trying to avoid the collision is by using the request to send and the clear to send. So when we send when the source sends the request to send signal, it actually announces to the nodes in the proximity that it wants to send data to a particular destination. So the address of the destination is actually part of the RTS, and the duration of the data, including all the required SIFS and the CTS, and so the entire period of the transmission is actually announced in the RTS. So when the nodes listen to RTS, the destination will recognize that this transmission or this request to transmit is targeting this node, and all the other nodes will encounter or will go into a phase called NAV, or network address vector, where they refrain from transmitting anything or sensing or doing anything during that transmission. As we said, some of these nodes will not listen to RTS necessarily, in which case the destination will send a clear to send. A clear to send signal will be sent back to the source, and in that case, some other nodes may listen to this CTS, and they will also go into NAV period. As we can see here, if we can consider that the interframe spacing is used for priority, okay, because that's what's going to happen later on. Which type of frames are more important, or they have higher priority? The initial transmission or the RTS and CTS? Okay, so if a new node here that did not listen to RTS wants to send, okay, send data, for example. So will the data frame have higher priority, or the CTS have higher priority? CTS and RTS, why?
Because it guarantees access to them.
Because of the short interframe spacing. So the short interframe spacing, if you have any node that tries to initiate new transmission, this node will have to wait for DIFS, right? Whereas the source that already engaged in the transmission will send CTS. So even if you don't listen to RTS and you try to engage into a new transmission, chances are you will hear the CTS before you try to engage into a new transmission, right? Because of the fact that here we have short interframe spacing, which is shorter compared to DIFS, which means that most probably the node that tries to initiate a new transmission will listen to CTS and will stop or refrain from transmitting anything before it actually starts. So that's another reason why we have short interframe spacing between RTS and CTS. Because if you have engaged in a new transmission, you have the priority to finish it to the end, okay, rather than another node starting a new transmission from the beginning. Okay. Okay. So if some of the nodes did not listen to CTS, which is less probable, but just in case, then they will listen to the data, in which case, whenever you listen to RTS, CTS, or data or something, you have to refrain from transmission. Okay? So that's the time diagram or the timing sequence of the actual transmission process from the beginning to the end. And as we said, there is no guarantee that there is no collision that will happen during this process. In which case, if a collision happens, then both nodes will go into a back-off procedure. In the back-off procedure, we have to wait for a random period of time, and this random period of time is proportional to a specific window. We call it a contention window, okay? And hopefully next time one of them will have access to the medium before the other, and they will not go into the same process again. Okay? So as we said, the short interframe spacing is used as the interframe spacing between data frame and its acknowledgement. So once we engage into a new transmission, okay, inside that transmission, we always use short interframe spacing to make sure that CTS, data, acknowledgement, they all have higher priority than a node that tries to send for the first time, in which case this node will have to wait for a DIFS, which is a longer in terms of time, and this indicates that this node will have lower priority. There is another type of interframe spacing which we call PIFS. So D here stands for DCF and P stands for PCF, right? So D is the distributed coordination function, and P here stands for PCF, or point coordination function. As we said before, point coordination function is an optional mode of operation for 802.11, which leverages polling. In which case, can we have PCF for ad hoc networks?
No, we don't have centralized.
Why?
We don't have centralized control.
Okay, because we don't have any centralized control, right? So PCF requires a centralized controller, or they call it point coordinator, or PC. And this PC is usually implemented inside the access point, okay, to organize the polling and which node should send at any point in time, okay? So there is a PIFS, which is similar to DIFS, but it's used for PCF operation or PCF mode, and DIFS is DCF interframe spacing. Okay? So why do we have two different things? Is that, well, you could have some co-located cells. One PSS is engaged in a DCF mode of operation. The other one is engaged into a PCF mode of operation. And through sensing, you can sense the traffic, and based on that, you can decide whether you transmit or not. And depending on the PIFS or DIFS, some of these nodes will also get priority more than the others. Usually, PIFS is a little bit shorter than DIFS, which means that PCF will have higher priority, slightly higher priority than DCF. Okay? So if some nodes are engaged into a PCF mode, they may probably gain access to the medium before a node that's engaged in DCF. Okay? Usually, yeah. Okay? But the standards does not enforce that. So again, PCF is an optional mode of operation, which is a collision-free mechanism, and it leverages, it's only used for infrastructure mode, and it uses the point coordination or the point coordinator, which is implemented as part of the access point. and it uses a centralized polling mechanism. Theoretically speaking, can PCF provide quality of service or not? So can DCF provide quality of service or not? The DCF implemented as part of 802.11. Can it provide any quality of service? In other words, can it provide service differentiation? And if the answer is yes, can it provide some guarantees on the actual delay and things like that, or not? DCF, can it provide quality of service? Why? I don't want it to be just a guess. Why? Because through the DIFS, there's no way of having any service differentiation between the nodes. All the nodes will have to wait for DIFS. Okay, if they are engaged into transmission, they have to send RTS and CTS and so on and so forth. So there is no distinction between the nodes in any way. Okay? There is no clear mechanism that distinguishes between these nodes, that gives one node more priority than the other. We didn't talk about anything that would make this possible. Okay? We didn't talk about any priority scheme or any kind of distinction or anything that will give one node more priority than the other. Okay? Unless we control the IFS for certain nodes, in which case we can, but DCF itself does not do that. Okay? And that's what we will talk about as part of the extension to 802.11. So, okay, so the next question is, can PCF provide quality of service or not? Based on what?
We can control the access duration for each node.
Okay.
So if we want to give a priority for a certain node, we give it more time to access the...
Okay. Through controlling the polling sequence and the polling duration. So when I pull, I can say, you talk now, and you can talk for 10 minutes. And then next, you can talk now, but you can talk only for 1 minute. In that case, I provided some service differentiation, right? So theoretically speaking, PCF can provide not only service differentiation, but it can actually provide some predictable performance. Why? Because collision is eliminated, right? So by controlling the sequence of pulling and the duration, I can control exactly the performance of a certain node by giving this node very high priority and specific duration, in which case I can control how much delay this node will encounter, how much throughput, and so on and so forth. Okay? However, the standards itself does not dictate any polling sequence. Okay? The standards does not dictate any polling sequence. There is a huge amount of research that has been done for different types of polling sequence that will guarantee quality of service in terms of service differentiation and predictable delay and throughput. But the standards itself does not dictate that. Okay? So theoretically, PCF can be used for quality of service. However, this is not part of the standard. Okay? With regards to the physical layer convergence protocol, we talked about PLCP as a sublayer in the physical layer, right? So we said that the physical layer is composed of two different sublayers. One is PLCP, and the other one is the physical layer medium-dependent sublayer, which deals with all the signals and all the analog, transmission, which is heavily dependent on the medium. That's why it's called medium-dependent physical or sublayer. So this is the sublayer that deals with all the types of signals, the symbols, the transmission, whether we generate an electric signal, if we're talking about wire, or microwave signal, if we're talking about wireless and fiber optics, or optical signal, if we're talking about fiber optics. So the PLCP layer, as we said, it acts as an interface between the data link layer and the medium-dependent sublayer. And one of its functions is carrier sensing. So here is where we do a carrier sensing. So for carrier sensing, the standards defines 5 different modes for carrier sensing, which differs in how carrier sensing is performed. So for carrier sensing using mode 1, what happens is that the PLCP will use a certain threshold. Okay, and this is the power. So it actually tries to sense the power on the medium, and if the power goes above certain threshold, even for an instantaneous period of time, then it triggers the fact that the medium is busy. Okay? So this is a very simple mode. It's energy-based detection. Okay, it's solely energy-based detection, so it doesn't actually use any kind of sophistication, or it's simple. Energy detection is actually one of the most common techniques for carrier sensing until today, because it's very simple. However, as we can see, it's not necessarily very accurate. Why? Because some noise can get instantaneously very high values. Okay. If you have lightning or thunder or something like this, okay, so you can get, they call it impulse noise. So these type of signals may be detected that the medium is busy, and will in fact force you not to engage into transmission or anything. Okay, so to resolve this issue, there is the mode 4, and again there is mode 2 and mode 3, by the way, but we don't have to talk about them. So CCA mode 4, this actually uses a timer, because one of the drawbacks of this method is that it uses threshold, and threshold focuses on the value, but it does not focus on the time, in which case we care about what is the duration. Okay, so we need to maintain above certain threshold for a certain period of time. That's when we are sure that there is really a signal being sent. Okay, so but actually in mode 4 we don't use any threshold on the value. We use timer. And during this time, we just count the number of changes in the value of the signal, the number of changes only, for a duration of time. So even if the signal is like this, okay, we might actually detect that there is a signal being sent, even if the signal value is low. Okay? So even if the signal value is low, but for a duration of time, there is some changes in this signal. Okay? So for me, there is the medium is busy in that case. And of course, as you can see as well, that may not be the most accurate way of, because again, noise changes throughout the time, and it can actually trigger some busy signals, although it's just noise. There is no actual signal being transmitted. So that's why mode 5 tries to combine the two methods into using a timer as well as a threshold. So for a duration of time, you count the number of times that you have gone beyond the threshold. Okay? So by using these two methods, you can get to a very high level of accuracy for detecting the signal on the median. Okay? So these are different modes of operation that's used as part of the standard, as part of the PLCP sublayer. Okay? Any questions here? So it's so there either a threshold on the value or a duration on the time, and mode 5 actually combines both of them. So the question now is that we need to go back to all the aspects of quality of service that we have studied so far, and let's analyze whether the standards actually provide any mechanism that will make such quality of service components viable or possible. Okay? So the first thing we talked about is classification. So do we have any way in the standards that can facilitate the fact that we classify the traffic? And the standards actually does not talk about anything related to any distinction between the traffic. So just the fact that we use DIFS and SIFS and these kind of things, that doesn't mean that because here classification is, it tries to distinguish between the traffic that is coming from different nodes, remember, okay? And classification, as we said before, is the first step towards providing service differentiation. So first we have to classify whether the incoming traffic is audio, video, and because based on that, we can assign a specific quality of service level to this type of traffic. So, so for DCF, there is no actual classification, and therefore, we cannot provide any service differentiation at all in DCF. So that's a done deal. Regarding channel access mechanism, because we use CSMA CA, we know that CSMA CA is collision-based, so there is some possibility for collision in that case. So we know that for DCF. For packet scheduling, these are the components that we talked about. Remember, these are the components that we talked about for quality of service mechanisms. If you go back to quality of service mechanism chapter, you see that these are the techniques or the components that we talked about in order to realize any kind of quality of service levels. So channel access, we use CSMA CA, so we can identify that. So for packet scheduling, there is no priority scheme here, right? Which means that the traffic that is coming from within a particular node will take a first in, first out kind of scheduling. So the intra-station here, we mean that if the traffic inside one node, okay? So for example, if we have two different streams, one audio and one video coming on one node, okay? Does the standard talk about anything that will have a separate queue or separate kind of performance for audio versus video? We didn't talk about that, right? So in that case, the intra-station packet scheduling is actually using one queue, and in that case, it's first in, first out. So there's no special mechanism in that case. Okay? What about BCF? So again, well, here we're talking about what the standard provides, right? Not what we would hope to do. Okay? So in that case, we can find that BCF does not actually provide quality of service the way that it's designed now, because the standard, separates the polling sequence as out of scope of the standards. So there's no actual classification in PCF. We cannot distinguish between audio and video. So in that case, there is no service differentiation. The channel access mechanism here is polling. So we know that, which is collision-free. So theoretically speaking, with collision-free protocol, we can provide some quality of service. However, the standard does not dictate a specific polling sequence, in which case we cannot provide quality of service as part of the standard. And for package scheduling, due to the lack of the classification mechanism within each station, still intra-station package scheduling still uses FIFO as well. Okay? So with that, we know that the baseline standards does not actually give us any way of providing quality of service with its two major components. We need service differentiation, and hopefully we need some guarantees on the delay and throughput and so on and so forth. Okay? So the standard itself does not give us this. So in order for us to be able to provide quality of service in PCF, which again is not part of the standard, in that case, we hope to have some algorithms to determine the polling sequence. If we have this, then we can provide some service differentiation. Okay? So we would hope to also have algorithm to determine the duration of contention-free periods. Remember that we said that the access point sends a beacon signal at the beginning, and then it starts, and there is another beacon here, and here in the middle we can control the duration of PCF versus DCF, right? And this boundary here can move back and forth, right? And we know that DCF does not provide any service differentiation, okay? But PCF is optional. So if we have an algorithm that can, somehow understand the requirements of each individual node, and based on that estimate the duration of PCF with regards to DCF, okay? So if I have no multimedia requirements, for example, then I don't need any PCF because it's optional. If I have some requirements on multimedia, for example, for stored multimedia content or something, then I can calculate the duration of PCF that I need. If I have an interactive kind of application like video conferencing or audio or voice chat or something like this, then again I can increase this or decrease this based on the requirements. Okay? We would love to have an algorithm like this, but again, the standards does not define anything related to that. Okay? And of course, all of this will only become a reality if you have quality of service signaling, because if you don't have quality of service signaling, you have no way of understanding the requirements of the node, right? So each node has to kind of formulate a signal or formulate some control information which tells the access point or tells the other nodes what is the requirements of this node in terms of multimedia and streaming requirements, and what is the delay expectation, what is the throughput expectation, and so on and so forth. Again, quality of service signaling is not part of the standards. The standards does not define anything related to quality of service signaling. Okay? So these are some of the things that we would hope to have in the standards that 802.11 does not provide. And that's why we need to shift gear to an extension to 802.11, which hopefully can give us all these components, and if not more. So the 802.11e is another variation of 802.11 family, which is designed with the perception of quality of service in particular. So So the standards, tries to achieve two major objectives, okay, which are related to quality of service. So first is service differentiation. So we need to have some service differentiation between the nodes. And as we said, that one of the ways is through varying the PCF period. And even with DCF, can we provide some service differentiation? Through what? DCF is not polling, come on. Huh? What? Huh? The back off time, bravo. Yes, back off time, yes. So I can control the back off time, in which case I can give more priority to one node versus the other. And what else? I can control the duration of DIFS, okay? Because if some nodes have shorter period of, because as we said, the CTS and acknowledgement and data, they have more priority. Why? Because they have to wait for only short interframe spacing, SIFS, right? So I can sort of generalize that concept and say, okay, I can give more priority to certain nodes by changing the IFS for these nodes, right? So the nodes that will have less DIFS or shorter duration for DIFS will gain more priority to access the channel. Okay, so all of these are techniques that we can use to provide some service differentiation. Quantitative quality of service, though, is going to be very tricky for DCF. You cannot provide any guarantees on the quality of service in terms of providing predictable delays and throughput in an environment which is full of collision. Because collision is not something controllable, right? So we cannot control when the collision is going to happen, because if we know when the collision is going to happen, we can avoid it easily. But the problem here is that we don't know when the collision will happen. If we don't know when the collision will happen, then we are in a very unpredictable environment, in which case we cannot give any guarantees. So this is the fundamental issue here. For PCF, we can, because there's no collision, right? So I know exactly the duration of the contention-free period, okay? I know, I can control the polling sequence, right? I can control the duration based on which I can pull any node, in which case everything is under control. Yeah. Everything is controlled. So there's no randomness in that case. Well, in a way, the only randomness here is the channel. But there is no significant level of randomness here, in which case we can provide some guarantees. Okay? So quantitative quality of service is possible only for PCF, not for DCF. But both of them can give us a service differentiation. معايا ولا الناس are you following ولا في ناس واقعة ولا following ولا it's okay يعني? Okay. So the quality of service mechanisms in 802.11e, they provide some traffic classification. So we need some traffic classification for 802.11e. That's one. We need to provide, hopefully, some new channel access and scheduling mechanisms, which can give us more granularity to provide quality of service. For sure, all of this will not become possible if we don't have quality of service signaling, because if we don't know the requirements and the needs of the nodes, how can we perform classification? How can we perform some specific polling mechanism or polling sequence, or specify the duration of the polling or something like this? We need to know the requirements of the node first before we can design anything related to providing quality of service. So quality of service signaling is a very important component that must be there. And we'll talk about some new frames for quality of service support that we will talk about. So 802.11e provides these traffic categories, okay? So it provides around 8 different traffic categories, or what we used to call traffic classes. Okay. So these traffic categories, they define specific level of service. Okay. Whether it's like best effort. For best effort, as we said, best effort is something that, or a queue that I can serve whenever I don't have anything else to do. So this has the lowest priority. Okay. There is a background traffic which has like maybe slightly more priority, all the way until we have video or voice. So voice has more priority than video, because voice, as we said before, voice requires more predictable type of delay requirements more than the video. Specifically, if video we lose some packets, they will have less effect versus if we lose some packets from voice. So voice is both delay and loss sensitive, okay, compared to video. Video is loss insensitive, but it's delay sensitive, okay. And at the end there is like some network control functions which will have the highest priority. So starting from 0 all the way to 7, we have 8 different traffic categories. And remember here that traffic categories are classes of service, in which case can we assign more than one stream to any of these categories, or we have to assign one stream to one category? Is it a one-to-one relationship or many-to-one relationship? Many-to-one relationship. Which means that these traffic categories, remember, they provide a per class or per flow quality of service? Per class quality of service. Okay? Per class quality of service. So typically, I assign multiple streams, whether voice, video, data, graphics, something like this. I assign multiple of these streams to one of these classes based on some classification that I have to do at the beginning. And again, in order for me to perform classification, I need some kind of quality of service signaling. I need to assess the requirements of each node, and based on that, I can perform classification, and I can map a specific stream to a specific traffic category in this list. Okay? So any questions? So that's the first thing that 802.11e defines, which is not part of 802.11 at all. Okay? So these traffic categories, they provide per class quality of service. But the standards did not stop at this level. Actually, it defines also what we call traffic streams. So traffic streams are separate traffic streams which can, so a traffic stream can represent like one voice traffic, or one video traffic, or one graphics, or one data traffic, and so on and so forth. And each traffic stream can have a separate type of service. We call it a traffic stream service, or a T-spec. So every traffic stream has some descriptive or some description, which is what we call traffic spec. The traffic spec here, or the traffic specification, describes what is the average throughput, what is the maximum throughput, if it's a constant bitrate stream or variable bitrate stream, what is the delay requirements on this stream, and so on and so forth. Why is this? Because I need to also provide, in addition to the per class behavior, I need to provide some per flow behavior. So the standard actually defines both.
Traffic stream is traffic flow?
Yes, traffic stream corresponds to the flow that we talked about before. In which case, I can have more per class behavior and per flow behavior. That's as far as 802.11e is concerned. Remember, here the pair flow behavior is at the level of the BSS. So at the BSS level, not at the core network level. Because as we said before, integrated services that provides pair flow behavior is actually very non-scalable in the core network, right? Because we cannot maintain these traffic specs in the core network. It will become very non-scalable, right? Because at the core network, you have millions of these T-specs. And you cannot have core routers in the core network to maintain all these T-specs at the core network level. It's not feasible. But at the level of the BSS, we could do that. So T-spec, because at the level of the BSS, we can have how many nodes? 100 nodes? That's fine. It's reasonable, right? But if we do that at the core level, at the core network level, is not possible. So that's why 802.11e reasonably defines traffic stream behavior or pair flow behavior to them.
So you can, for the Cont, can give you service differentiation only for 8 streams, their BSS?
For what?
8 streams?
No. Did I say that? Well, for traffic categories, we can have only 8. Did I talk about any 8?
No, like in the traffic categories, we have
8
categories.
8 categories, 8 classes.
8 classes.
Right, and each one may have multiple streams or multiple flows in that case, because there is a slight difference between a stream and a flow. A flow corresponds to voice flow, data flow, video flow, and so on. Stream is a terminology of the standards. A stream here is a flow that is described by a traffic stream specification. Okay, it's a logical stream inside the standards that can have a separate, behavior or a separate service level at the flow level or at the stream level. Okay. So a stream is a terminology inside the standard which maps one-to-one to a flow, right? But in the standard, in order to know the requirements of this flow, we have what we call a T-spec. The T-spec describes that this flow requires this amount of throughput, this amount of delay, this amount of maximum, minimum, statistical kind of quality of service requirements. Remember? The statistical type of quality of service quantitative requirements and so on. Because all these T-specs, okay, will allow me then to provide pair flow service level or quality of service. And this, of course, can become possible using PCF. So for PCF, I can have control on the duration of the PCF period based on some information from here. I can decide then that I need this amount of PCF period, and during this PCF period, I can design also the polling sequence based on which traffic stream will have the highest priority, which one comes after it, and so on. Okay. And because I have no collision, I can provide some guarantees on that side. But here, the traffic category can be provided easily using DCF. So DCF can actually provide this. So using DCF, you can assign different categories to a specific DCF in terms of, as we will see later, in terms of what is the DIFS used at that level, and what is the contention window period, how the back office is actually performed at this traffic category. Okay. So the 802.11e defines what we call hybrid contention period, or the HCF here. Sorry, hybrid contention-free period. Okay, hybrid contention-free period, and we'll talk about why we call it hybrid and not use PCF itself. as is. But this is like a generalized PCF mode of operation. Also, we notice here that even during the contention period, I can have some periods of HCF. So unlike the 802.11, because here I can provide some traffic category or per class behavior, and in some cases I need some HCF periods even inside the contention period. Okay? So here, EDCF stands for Enhanced Distributed Coordination Function. So the DCF mode of operation, which was part of 802.11, here is actually enhanced, and we'll talk about how is this enhanced through basically the priority schemes that we have talked about, through changing the IFS and changing the contention window period and so on and so forth. Okay? So that's how the EDCF looks like. So instead of, so we know that we have to wait for a DIFS, okay, and if the medium is busy, then we go into a back-off procedure, and then we have to wait for when the medium becomes idle again, and then we have to wait for DIFS and so on and so forth. Here we have extended the DIFS into what we call arbitrary interframe spacing. Arbitrary interframe spacing. So here, AIFS will have 8 different values corresponding to the 8 traffic categories. So I will have AIFS TC0, which will be the longest in that case, because the longest will have the lowest priority, and AIFS of traffic category 7, which will have the shortest wait time, okay, the shortest interframe spacing. So we call them a arbitrary interframe spacing. So I can assign, based on the classification process, I can assign a specific stream or a specific traffic that is coming from one node into one of these traffic categories, in which case this node will have a certain AIFS. So depending on the AIFS of that node, this node will have high or low priority in gaining access to the channel, on average. Because again, there is something here that I cannot control, which is the collision. I cannot control. Okay? So we'll talk about this again.